So the first section we're going to look at is Introduction to Power Functions. And the key concepts that we're going to look at are a power function is the simplest type of polynomial function, and it has the form f at x equals a times x to the power of n, where n is a whole number, x is the variable, and a is any real number other than 0. So some important characteristics. Some power functions have special names that are associated with their degree, and we're going to look at some of those in the next couple slides. The degree of the polynomial is determined by the exponent of the greatest power. Another thing we're going to look at is the end behavior of the graphs of these functions. And what that means is we're going to look at what happens to the y values as the values of x increase and as the value of x decrease. And just remember that a relation is a function if for every x value there's only one y value. And remember that we can test that using the vertical line test, for example. So let's look at determining the degree of the power functions. So the first one we're going to look at here, we got y equals a. So a is just a constant, and obviously there's no variable there. So if there's no variable, then we have a degree of 0. Second one we have here is y equals a times x. So if there's no number in the exponent there, we just assume that it is a 1. And if it's 1, that means we have a degree of 1. And this is just your basic linear equation. Next example, we got y equals a times x squared. So the only variable is x squared. So we have a degree of 2. And obviously, from grade 10 and 11, you will remember that this is a quadratic. Third example here, we have y equals a times x to the power of 3. So this would have a degree of 3, and we call this one cubic. There's a few others that you will be familiar with as well in this section. So x to the power of 4 would be quartic, and x to the power of 5 would be quintic. So let's determine the degree, and let's look at the leading coefficient of a couple of examples here. So the first example we got is this one here, with y equals negative x cubed plus 8x minus 2. So what is the highest exponent there? We got x to the power of 3, so that would mean we have a degree of 3. And let's look at the leading coefficient of that. We have a negative out front, so that means it's a negative 1. Let's look at the next example here. We got y equals x squared minus 4x to the power of 5, subtract 2. So we have to be careful here. So normally when we arrange these variables, we do it from the highest to the lowest. But in this case, it isn't done like that. So we have to be careful. So if we look for the highest exponent, we have x to the power of 5. So that means we have a degree of 5. So if we look at the leading coefficient of that variable, out front here we have a negative 4. So that means our leading coefficient is negative 4. And our degree is 5, because 5 is the highest exponent on the variable. Last example. This time we do have all our exponents in decreasing order. So we have a degree that's 4, and the leading coefficient here is positive 1/3. Okay, so just to make some connections here, A few more things that we're going to look at. So one being line of symmetry. So you've seen a line of symmetry before when we've looked at quadratics. So a line of symmetry divides the graph into parts that so that one side is a reflection of the other side. So it cuts it into two equal parts. And the other one we're going to look at is point of symmetry. So a point of symmetry occurs when one half of the graph can be rotated 180 degrees to coincide with the other part of the graph. So another important characteristic or feature that we're going to look at is the end behavior of the graphs of polynomial functions. So what we're going to do is we're going to look at some examples, and we're going to look at what happens to the y values as x increases or x goes to the right or x approaches infinity. That little symbol there is the symbol for infinity. And we're going to look at what happens as x approaches negative infinity, so as it goes to the left. We're also going to state the domain and range, and we're going to see if we have a line of symmetry or a point of symmetry. So we got two examples here. The first one we got y equals negative x. So that's just a linear function. The second one we got y equals half x squared. So we got a quadratic. So let's look at the first one here. So as x approaches negative infinity, what is happening? As we go further and further to the left, well, the y values are getting bigger. So we say y approaches infinity. So as x gets further to the left, y goes further up. And what happens as x approaches positive infinity? So as x goes further and further to the right, y is getting smaller. So y approaches negative infinity. So as x goes to the right, y is going down. So let's look at our quadratic here. So as x values increase negative or approach negative infinity, as they go further and further this way, y values are getting larger. So as we approach negative infinity, y approaches infinity. And what happens when we get x going further to the right? So as x approaches infinity, y still approaches positive infinity. So now we're going to look at the domain and range. So if we look at our linear function there, the domain and range are pretty simple. So we got a domain that is x is an element of R and a range where y is an element of R. How about for our quadratic? So for our quadratic, we have x is an element of R, but we have a restriction on the range where y must be greater than or equal to 0, because that's the vertex. And last thing we're going to look at here, so for our line, we have a point of symmetry. And for our quadratic here, we have a line of symmetry about the y-axis. So what I want to show you here is the point of symmetry. So if we look at the origin as being our point of symmetry, if we rotate 180 degrees, there you go. So the graph coincides with itself. So third example here. So we got a cubic function. So we have y equals 4x cubed. So let's look at as x approaches negative infinity. Since x approaches negative infinity, our y values are going smaller and smaller. So we say y values decrease. So y approaches negative infinity. And as our x values approach positive infinity, our y values get bigger. So y approaches infinity. So our domain and range are pretty simple. We got x being an element of R and y being an element of R. And you will notice we have a point of symmetry here about the origin. And if we look closely, so we rotate it 180 degrees, coincides with itself.